My name is Matt. I work at Square on Square Cache, and today I'm going to be talking about building camera features. So you have the task of adding a camera feature to your application. It might be something simple like a profile picture. It might be something a lot more complicated. There's a few different ways to go about doing this. And right at the start, you need to ask yourself, how much work do you want to do? So let's do a little foreshadowing here. First option is to just do a camera intent. So for this, you create an intent, you launch it, and it will open whatever camera app the user prefers to use on their phone. Then they'll go through that app to take a picture, and then eventually you'll get a response back with the image that they've captured. So this is like really easy. It's like 10 lines of code. You don't have to deal with the camera at all, and you get an image back. Downsides here are you have no control over the UI. So this is not your application, it's not your process, it's all done by a different app. You also have no control over the hardware. So basically it's up to this other camera app to interact with the hardware, change things like focus, exposure, all that kind of stuff. All right, so next option, if that's not enough for you, is you can use the library. And here we're starting to move into like the days time frame. However, this can easily stretch to weeks depending on what you actually need to do. So with the library, a lot of the code is written for you. And ideally, the API lets you configure a few things and then get images back. But depending on the library you use, it can be a lot more complicated. The downside is that any changes you need to make or any fixes require that you understand basically the entire code base because it's really complicated. And you make one change and anything can go wrong. So here are a few libraries that exist right now. The one at the top is iterate. It's the latest one that I've seen. The API is really solid, but I haven't had time to play with it, so don't really have an opinion on it yet other than the API. Then there's a few others there. So I'm giving this talk because these options were not sufficient for us at the time. So the next option is to do it yourself. And here, this is going to take you weeks probably, but I mean, you can go on to months. You can spend the rest of your life writing camera apps or camera code. So the remainder of this talk is going to be basically my 2017. So doing it yourself, you have full control over everything. You're interacting with the camera hardware yourself. You can do whatever you want, but you need to write everything. And when you're writing all this, you will be surprised. So you will probably get Samsung'd, or in our case, you will get LG'd. All right, so cameras. How do they work? All right, so you see a cat. Cat's doing something really cute because it's a cat. And you decide, I'm going to take a picture of this and post it on the internet and get all the fake internet points I want. So you pull out your phone, point at the cat, and you take a picture. So what's happening here? Well, you have a light source. In this case, the cat's outside, so you got the sun. It's going to emit light. That light bounces off the cat, heads towards your phone. The camera picks this up. You see a preview in your phone, and the display emits more light into your eyes, and now you can see the cat. But this is a talk about cameras, so we have to go deeper than this. Now, there's a lot going on inside of your phone. So light comes from sun, bounces off the cat, and it heads towards the camera hardware in your phones. This is going to go through a series of lenses and filters and other things to transform and filter the light, and ultimately it delivers it down to your camera sensor. Now your camera sensor takes this light information and it converts it into data. And this gets sent up through the application, which then sends it to the screen, which then transforms it back to light, which gets picked up by your eyes. All right, so I'm going to take some time here and I'm going to talk about color formats. Now, normally, when you're not dealing with cameras, you're operating on data that's already been decoded for you. So you're dealing with bitmaps, you're dealing with canvases. And with the camera, you are operating on a format exposed by the hardware. So you're operating on encoded data. And this was really uncomfortable for me at first, but I got a lot more comfortable watching Jesse's talk from droidCon last year. All right, let's talk about RGB. This is a format we're all used to on Android. Stands for red, green, and blue. You have three color channels. So we have an image here, and in RGB, it's split into these channels. You have red channel, green channel, and a blue channel. Now another format is RGBA, which is just RGB plus another alpha channel. And frequently on Java and Android, this is in the order of ARGB. So a new one potentially is YUV. And unlike RGB, this is not an acronym. It doesn't really stand for anything. And the history of YUV is fairly interesting. So it was invented when engineers wanted to add color to the existing black and white television infrastructure. So they already had black and white, and they had to add color in a backwards compatible way. Now, when referring to YUV in a digital context, we're typically talking about YSDBCR, but the terms are used interchangeably, so it's kind of confusing. But just, if you see YSDBCR, it's basically the same thing as YUV. So, like RGB, there's 3 channels. First channel is your luminance channel or your brightness. So this is just the grayscale data coming in from your image, the brightness. And the next 2 channels are your color channels. These are the chrominance. First one is your blue-yellow, and the second one is your red-cyan. So take a look at our image from before, and represented in YCBCR, it looks like this. We have grayscale, and we have the bluey yellow, and then the red-green split. All right, so why am I talking about YUV? Well, the simple reason is that it's what the camera is going to give us for the preview. But why does the camera give us that? There's a few reasons for that. So this is a diagram from earlier about the light. And these sections here, the information is traveling as photons, traveling at the speed of light. It's basically traveling as fast as possible. But then when we get here, the sensor is encoding this light information as data and sending it up through the application. And what we want to do here is we want to get this data from the sensor as fast as possible. And we need to get this data from the sensor to the screen as fast as possible. And one way to do this is to just sample less data, so you get a lower quality image. So there's different ways to represent a bitmap. With RGB, the one that we are used to is RGB 888. And what these numbers indicate are how many bits each channel gets to represent a pixel. So red channel gets 8 bits, green channel gets 8, and blue gets 8. So this is where the numbers 0 to 255 come from. So a pixel will be stored in 24 bits, and a 1920 by 1080 image will take up about 6 megabytes. And if you're trying to render a camera preview at 60 frames per second, you're sending 360 megabytes per second to render an RGB 888 image. All right, so we can cut this in half. We can go to RGB 444. So every channel gets 4 bits. A pixel, it fits into 12 bits. And a 1920 by 1080 image is now 3 megabytes. So to get a 60 frame per second preview, we're sending 180 megabytes per second. Now, another format I want to talk about, because it's fairly popular, you might come across it in your travels, is RGB 565. And now the constraint for this is that we need to fit information into 16 bits. So if you were to split this up across all the channels, you would have 5 each. We have 1 extra bit remaining. And the decision was made to give it to green. Now, why does green get this extra bit? Well, it has to do with our eyes. So CIE 1931, this is the standard that defines the visible colors. And this is a representation of it. And it's not entirely accurate right now because my laptop's doing color correction and the projector's doing color correction. But you should be able to see that green is significantly larger than red and blue. And that's because our eyes are much more sensitive to green light than red and blue light. So that is why green gets the extra bit. Fun fact. All right, let's talk about YUV. Now, a high-resolution YUV image is 444, and these numbers mean completely different things than RGB. They represent the resolution of the color channels. So the first 2 numbers are your horizontal resolution, and then the second and third numbers are your vertical resolution. So for 444, all the numbers are the same, so we have a full resolution image. So just like RGB, every channel gets 8 bits here, 24 bits per pixel, and our 1920 by 1080 image is 6 megabytes. Now, let's talk about YUV 422. So we can see here that the second number is half of the first number, which means that we have half horizontal resolution in our colors. Then the last two numbers are the same, so we have full vertical resolution. And what happens here is that every color sample from the sensor is used to color 2 pixels in the luminance channel. So every channel still gets 8 bits, but the color channels are spread out over 2 pixels. So per pixel, the CB and the CR channels use 4 bits instead of 8. So we have 16 bits per pixel, and our 6 megabyte image is now 4 megabytes. We have full resolution luminance and half resolution color. Next step down from here is UF420. Once again, 4.2 means that we have half horizontal resolution in our colors. And the 2.0 here, it's not actually a ratio. All you need to know here is that if the third number matches the second number, it's full resolution. If it's 0, it's half resolution. So 420, we have half vertical resolution. And now every color sample is used to color 4 pixels in a 2x2 grid. So how this works out so that every pixel has 2 bits of CB and 2 bits of CR, still full resolution luminance. So we have 12 bits per pixel, and our 1920 by 1080 image is 3 megabytes. So that was exactly the same as RGB 444. Why am I talking about UF420? Well, once again, this has to do with our eyes. The human eye has very little sensitivity to color, but the brightness actually has a huge impact in how we perceive the detail of the image. So a UF420 image, even though it's a quarter of the color, we perceive it to be a higher quality image than RGB 444. And a bonus here is that because one of the channels is grayscale, a lot of the image processing that we would tend to do on this only needs to deal with grayscale images. We can just throw away 2 out of the 3 channels and only send 1 channel around. So if colors are of interest to you, I highly recommend Ramon's talk from I/O 2017. There's like almost 0 overlap to what I'm talking about, but I love that talk, so you should check it out. All right, so implementing camera APIs. There's 2 APIs for you to choose from. You have Camera1, and you also have Camera2. Camera1 was added SDK1 2009. It has relatively simple API for accessing the camera. I say relatively because it's still kind of complicated, but you really can't do much with it. They don't really expose a lot of the things that the hardware can do, but people wanted to write full-featured camera applications, so that's why Camera2 was introduced in 2014 with SDK21. It's very powerful, and you have full access to the camera hardware, but it's also quite complicated. So Camera1, it's available on 100% of devices, although it's deprecated as of API 21. And Camera2 is on 80% of devices. However, that is a worldwide number. So if you're kind of targeting North America or United States, then the percentage will be much higher. So for us, Camera1 lacked the hooks that we needed, so we're only targeting Camera2. So if you need to support both, you should check out the libraries that I mentioned earlier because they have backwards compatibility with both SDKs. So I'm not going to do a broad API overview of Camera2. It's been done before, much better than I can do it. Specifically, it was done by when droidCon here 2 years ago. But there are a couple things that I think are important to talk about. So we Android developers, we love our life cycles, and the camera also has a life cycle. So first thing that you need to do is you need to ask for permission if you're on Android 6.0 or up. Hopefully you get permission because you've justified it properly. And then you ask the system, what cameras do you have? Now the system's going to just tell you I have Camera1 and I have Camera2. Just going to give you some IDs. It could also give you 0 cameras, so you have to handle that. So now you need to figure out which one of these cameras you actually want to use. So we're going to ask the system, tell me more information about Camera1. And the system's going to say, it's going to give you a bunch of information, and it's also going to tell you it's a front-facing camera. Well, we're not taking selfies, we're taking pictures of cats, so we don't want a front-facing camera. So now we're going to ask about Camera2. All right, so we get some information back. It says it's a rear-facing camera. This is exactly what we want, so we're going to go with this one. So we ask the system, can you please open Camera2? Pretty please. And it's going to say, all right. But it can also say no, because some other application is using it. So hopefully it said yes, so then you ask it to start capturing an image. And it's going to say, OK. And it's going to start sending you preview information, all the frames it can get. And you're probably just going to send this to a surface view or a texture view. And when you do that, you're actually just going to crop the image, because it's going to give you a image of the resolution from the sensor, which doesn't actually match the resolution of the phone. So that's why sometimes when you take a picture, once it's taken, you'll see more in the picture than you're actually seeing in the live preview, which could be surprising to you. And the information that we're getting here is in YUV 420. So that's why I mentioned it earlier. Some cameras can give you RGB, but YUV 420 is universal. So if you're going to implement something, you should just implement that. And here is where we can optionally do some image processing on the frames that are coming in. So at some point, the user is going to say, that looks good. Please capture this. You're going to send that down to the system. And the system is going to give you a high-resolution image. And all of these can fail at any time for any reason, so you need to make sure you handle that. And you also need to make sure that you release whatever locks you're holding on the camera. So if you've ever opened up the camera app and it just says, I can't access the camera, it's because some other application grabbed it and didn't release it, and you should uninstall that application. So slides are not a good way to show or explain camera code. It's really, really dense code. So I recommend looking at libraries to learn about the code, or samples. So I've added the Google sample, Android Camera2 Basic. It's a great sample for figuring out what to do here. So I want to talk about strides for a little bit. This is something that caused problems for me at first because I wasn't expecting it. So when you get images delivered to you, they're going to be in one long byte array. And it's up to you to map that to a 2D representation for any processing that you want to do. So there's extra properties that you need to take into account for here when you're mapping this to like a 2D representation. The first is row stride. And this is the distance between rows in your array. So for this to be accurate, your row stride is 3. It's 3 bytes between 1 and 4. Now, if the row stride was 5, then this is basically what your byte array is going to look like. It's basically just garbage at the end of each row. It's not true for all formats, but all the ones that I've dealt with, it is actually garbage. Then the next one you have to account for is pixel stride. And this is the distance between each pixel in your byte array. So for this to be true, pixel stride is 1. Pixel stride is 2. Then there's more garbage in your byte array that you have to just ignore. And increasing the pixel stride also affects the row stride, so this is actually 7 now. And sometimes the data might be given to you without the final trailing pieces of garbage, so you can't rely on that size being there. All right, so I talked a little bit about processing. I'm going to talk about kernels now. And these aren't the OS kind of kernels. These are small matrices that can be used to do a variety of things, like blurring, sharpening, or edge detection. This is an example of an edge detection kernel. And what do you do with this? You do something called convolution. So here's an example image. It's a white arrow. And this is what it looks like on the luminance channel. And we'll take a look at the corner of the arrow here because it's interesting. So to detect edges, we're going to need somewhere to store our output. So we're going to create a new structure, but that's the size of the image. And let's start with this pixel right here. So we take our kernel and we center it over the corresponding pixel in our source image. And then what we do here is we multiply each value in the kernel by the corresponding value in the image, and then we sum them all together. So the result here is 0. This particular kernel gives 0 if the pixel and its adjacent neighbors are the same, and it gives a high value if they're different. So basically, we just iterate over the entire image doing this and filling out our output. And here is where we start actually getting towards an edge. where there's a difference between the black and the white pixel that we're currently looking at. And we keep going, and it's worth noting that we're taking the absolute value of the sum here. We don't really care if it's negative or positive. We just care about the difference. So we keep going, and we just fill out the entire image with this. And if we want to check our work visually, we can convert this back into an image. And we can see here that we've detected the corner of the arrow. So if we run this over the entire image, this is what we get. It is the edge of the arrow that we've drawn. So we can apply it to an actual picture here. And this is what it looks like. So it's a very edgy picture. There's lots of bricks. So what can we actually use this for? One thing you can do is you can take this and you can apply it back to the source image as a sharpening filter. What we used it for is for line detection. So suppose you're building an app that wants to confirm there's a debit card on the screen. We need to detect that there's edges that resemble the shape of a card. So this is our kernel from earlier. It's called a Laplace filter. We're actually going to swap that out with a Sobel filter. And this is less sensitive to noise, but it's very directional, so you need to have two of them. The first one here is detecting horizontal changes, and the second one is detecting vertical changes. And then you can combine the results doing this. One weird thing with kernels that I should mention, before you use them, you generally need to flip them horizontally and vertically. They're given in this kind of mirrored format for backwards compatibility with one-dimensional kernels. It's not the end of the world if you don't do this for most of the kernels, and actually with this particular one, it really doesn't make a difference, but just wanted to throw that out there. All right, so we apply this filter to our card, and this is what we get. We can clearly see that there are edges, but how do we teach a computer to see them? We use something called a Huff transform. So let's take a look at the bottom edge here. We have a bit of noise in our edge detection result, so you can set a threshold that you consider to be strong enough to be a line. And then for every pixel that meets this threshold, we're going to make a hypothesis that this pixel is on a line at 0 degrees. And then we do this for every single line that this pixel could be in. And after we've done this for all the pixels, we go and we look at our data, and we check the hypothesis or hypotheses and see if any of them actually worked out. So here's an example. We have 3 pixels, and we want to see if they're part of a line. We can see that they look like they're part of a line, but how does this work in practice? So we're going to start with a hypothesis that the first pixel is on a line at 135 degrees. Now, we need a way to identify the line so that we can record it. And we do this by taking the shortest line from our line to the origin, which is a perpendicular line, and we record the length of that line and its angle. This is an alternative to y equals mx plus b, but it works for vertical lines. And to save you from having to dust off that old trigonometry, this is the equation for the length of r. So I'm going to hypothesize that there is a line at all of these angles for all of these pixels. So we need to find r for all of them. So we're going to go through, we're going to record all this information, and we just get a whole bunch of numbers back. It doesn't really look like anything, but we can see here that for 75 degrees, it looks like we've actually found a line. They are all on the same 75-degree line. So if we run this on our image of a card and then we plot the results, this is what we get. I'm hoping the contrast is good there. This is plotted with theta on the x-axis and r on the y-axis. And we've actually found 4 clusters of possible lines here. So we can take this data and we can use it to draw lines back onto our source image. And look at that. We found the 4 edges of the card. So we can clearly see that it looks like a card, but how do we actually know in code that it's a card? So, we could do a whole ton of gross math. We can check aspect ratios. We can do a whole bunch of stuff. Or we can just make our lives easier and, draw a little box on the screen when we're taking a picture of this card to tell the user to put the card right here. And then we only look for lines in that box. All right, so you've written your frame processor, but you're only handling 1 frame every 5 seconds. What's going on? Well, you're writing code that processes millions of pixels, so every instruction matters. And I have some tips for cutting down on the instructions you're doing. So first, avoid copying. You may be tempted to take your really long byte array and map it into a two-dimensional byte array so that you can easily look up pixels at X and Y. I'm going to recommend you don't do this because this is just a lot of copying data around for like a really large image. So what you can do instead is you can create a wrapper around your byte array, and you can give it methods like get, which take in an X and Y, and they just do some math and map it to an index in the flat array. You can add things like rotate and crop, which all do things in place without actually copying data around. Avoid allocating. So you may be tempted to write functions like this, where you take in an image, you do some work on it, then you return another transformed image. Instead, you should be taking in the result as a parameter, so this can be shared and reused across all of the frames that you're processing. So optimize your kernels. So here's some code that does kernel convolution. As you can see, it takes in a kernel, it iterates over all of the values in the kernel, it does the multiplication and sums it up. We measured this to be really inefficient when we wrote it. The for loops all have overhead, and you're also wasting time on the zeros in the kernel. So we just inlined it. It looks kind of gross, but this was a significant performance improvement for us. And basically, this is why whenever you're looking at anything that deals with image processing or low-level stuff, it looks gross, and it's because gross code runs fast. So other tips, Kotlin inline functions are great here. So methods have another fixed cost, and on most of your work, it's all like that cost is dwarfed by everything else that's going on. However, when you're in a tight loop that's iterating over millions of pixels, and you're calling these methods, millions of times, that cost adds up. So one thing you could do is just get rid of those methods and inline all the code like I did with the kernel. But with Kotlin, what you can do is you can keep your functions, and then you tag them with inline. And when it gets compiled, it will basically just take that code and copy it to wherever it's used. So this increases your APK size, but it increases the performance of your application. So don't use it everywhere, but use it in places where you can measure a difference. Next is be lazy. Don't do a whole bunch of work transforming your images or anything like that until you actually need to do it. If you want to get crazy, you can push some of this down into native code, write some J and I wrappers, or even crazier, you can push it onto the GPU. So, quick iteration. I'm not talking about loops here. It's how can you build and test your code really quickly? So modules are a great solution for this. So this might be what your project looks like. You have basically an application module which has all of the logic for your app. You should take your camera code and you should pull it out into another library module. And what this does is it lets you cut down on your build times, because when you change code in this library, Gradle is only going to rebuild that library. And then, better yet, with this configuration, when you want to test it in your app, you have to run your app, and you have to get to the place in your app where you're actually using the camera code. So create a completely separate application that only runs your camera code. This is similar to how open source libraries work. They all come with like a sample application. Do this internally in your own projects so that you can very quickly build and test just the features you're working on. And we do this for things beyond camera. Any kind of complicated widget that we write, we split it out into a module, and then we create a sample application that only interacts with that library. So unit tests. You want to write tests that take in images, run your code, and print out or export new images. And you don't even need to test this automatically on CI for it to be useful. You can test it visually. And it lets you basically just take Android out of the equation. So when I started doing this, I would write code, and then I would install the application, and then I just kind of like hold my phone up and then try to debug while I'm moving my phone around, which is ridiculous. So, save some images, run them through your code, and then just visually check that your transformations and stuff are working. So I generated a lot of images for this talk. The code that I used to do this, I will put up on GitHub in the next few days. I need some time to clean it up. But yeah, so this will do like RGB splitting, and it'll do YUV splitting and YUV conversion, and the line detection and all that kind of stuff. Yeah, that's it. Thank you.